Hello everyone, I'm Zhe Chen, a postdoc from UCLA. Today, I would like to give our presentation entitled Blink, Bit-Sparse LSTM Inference Kernel Enabling Efficient Calcium Trace Extraction for Neurofeedback Devices. This work is in collaboration between computer science and psychology departments at UCLA. As the outline of the presentation, I will first briefly introduce the research background, and then present our proposed LSTM-based calcium trace extraction method. Next, I will propose the Bit-Sparse LSTM inference approach called Blink, which helps reduce circuit area and increase energy efficiency for the LSTM inference. Last, I will demonstrate the calcium image processing pipeline on FPGA based on the proposed techniques and enabling efficient calcium trace extraction for closed-loop neurofeedback applications. First, let's look at the research background. The calcium imaging is an emerging technique that can be used to monitor neural activity of a large population of neurons in vivo. The UCLA Miniscope is such a miniaturized calcium imaging microscope that can be implanted at a certain brain region of a running rat or mice while the animal is performing all kinds of behavior tasks. The UCLA Miniscope V3 device has a QVGA resolution with 30 frames per second speed, and it can monitor hundreds of cells simultaneously in a single session of data recording. As the Miniscope V3 is the most widely used one, there are a few types of miniscopes being developed with larger field of view and higher frame rates. With ever-increasing spatial and temporal resolution of the miniscope, the gap between the imaging and processing speed escalates. Recorded calcium imaging data are often analyzed offline, based on a method called CNMF, short for Constraint Non-Negative Matrix Factorization, which can simultaneously extract cell spatial footprints and temporal calcium traces from the calcium images, as the figure on the right shows. Although this method generates accurate cell trace extraction results, and the algorithm complexity scales linearly with the number of pixels processed, it requires iterative and batch processing, which make it hard to be used as an efficient solution for online calcium image processing in closed loop. Let's look at what a closed neurofeedback loop requires. Here, we focus on the online data processing component, which requires two important features for enabling efficient closed-loop feedback. One is the high energy efficiency, because this component may be eventually integrated into a head-mounted neurofeedback device that needs to run for days or even weeks on a single battery. The other one is the short processing latency, because it needs to generate quick feedback response at spike timing resolution at millisecond for closed-loop applications. So the motivation of this work is to leverage customized computing and algorithm hardware co-design to realize real-time calcium trace extraction with the accuracy close to offline method and high energy efficiency and short processing latency that can benefit the design of neurofeedback devices. Next, I'll introduce our proposed solution, the LSTM-based calcium trace extraction. A straightforward online calcium image processing pipeline can be made up of 3 consecutive steps: the motion correction, the image enhancement, and the calcium trace extraction. The motion correction is an important processing step, as it helps remove the motion artifacts caused by the movement of brain tissues during the image recording. Following that, the image enhancement plays an important role in removing the bulk of the background and increasing the signal-to-noise ratio of the calcium activity. Finally, the calcium trace extraction extracts calcium traces which reflect the activity of individual cells by applying the binary cell masks on top of the downsampled enhanced images. Such simple and direct calcium trace extraction from the enhanced images has a drawback on the trace extraction accuracy, especially for those cells whose fluorescence intensity and SNR are low. So in order to make this online trace extraction pipeline working, we have to address the challenge by increasing the trace extraction accuracy for those low SNR cells. The LSTM, short for long short-term memory, is a recurrent neural network machine learning model that has been successfully used in many time series prediction tasks. A single-layer LSTM model can be divided into 2 parts: the feed-forward pass and the recurrent pass. The feed-forward pass accomplishes the update of 4 types of LSTM gates: the input gate, the output gate, the forget gate, and the cell gate, while the recurrent pass performs the update of 2 types of nodes, the cell nodes and the hidden nodes. The most computational dense part lies in the feed-forward pass, which is the dense matrix multiplication. This slide shows our proposed LSTM-based calcium image processing pipeline and the implementation of each stage of the computation. First, the motion correction is realized by a frame-based cross-correlation against a reference image, and the algorithm and accelerator design have been proposed in our previous work. Second, the image enhancement is implemented by the morphological opening operation, which combines morphological erosion and dilation, and this algorithm has been proposed in previous literature. Third, the calcium trace extraction adopts a strategy combining the cell binary mask-based tracing and the LSTM inference. During the offline training, we take the traces extracted based on the cell binary masks as input and use the CNMF extracted calcium traces as the training target. After the training is done, we use the well-trained LSTMs to replace the acausal CNMF algorithm to perform the causal prediction. The causal prediction approaches to the accuracy achieved by the CNMF algorithm, whereas it avoids long latency caused by the acausal nature of the offline method. We compute the cross-correlation between the normalized online and offline extracted traces and use it as a measurement on how close the online extracted traces are compared to the offline traces. The figure in this slide provides an example of the normalized online and offline extracted traces from a same cell. We used the 1,000 frames of calcium images recorded from the mice using the Miniscope as the dataset for the algorithm evaluation. From a comparison between using or not using LSTM inference, 90.3% cell traces have increased the cross-correlation score after leveraging the LSTM inference, which means a general accuracy improvement in trace extraction. Next, I would like to introduce our proposed blink method. The blink is based on the bit-sparse data representation we proposed. In the bit-sparse representation, for an m-bit binary data, at most n bits can be freely set to be 0 or 1, whereas the rest of bits must remain 0. Since n is a value designed to be much smaller than m, we call this data representation bit-sparse. This figure shows two examples of the n over m bit-sparse data. In addition, we list another two examples of the 2 over 16 bit-sparse data, which can be converted to decimal format by decoding the bit-sparse data as a 16-bit fixed-point data. In fact, we evaluated and found out that the 1 to 8 over 16 bit-sparse data type can achieve significantly higher dynamic range than the 1 to 8-bit fixed-point data type on the LSTM weights after the training is converged. The bit-sparse quantization is performed by adding a bit sparsification stage inside the loop of the LSTM training. For every weight update loop during the training, the weights are first converted to the bit-sparse data type, and then they are used for the inference. This figure shows the flowchart of the bit sparsification. Bits are checked one by one from the most significant bit to the least significant bit. Once the count of n has reached, it rounds the value with the mathematical formula shown in this slide, which guarantees the converted weights comply with the bit-sparse definition. We quantized the LSTM weights on the feed-forward path with a variety of data types, including the floating point, the 16-bit fixed point, and 1 to 8 over 16 bit-sparse data types. And we evaluated the accuracy of the calcium trace extraction achieved under each case. We add the averaged sum of absolute difference between the online and offline extracted traces as another measurement of the accuracy. Evaluation results show that there is no accuracy loss as we gradually increased the bit sparsity up to the 1 over 16 bit sparse representation. Taking advantage of the bit-sparse representation, we are able to remove the multipliers on the feed-forward path of the LSTM inference circuit's design and replace them with simple bit shift operators. This figure shows the overall circuit's design of the bit-sparse LSTM inference kernel. The feed-forward path and the recurrent path of the LSTM inference can be fully pipelined, and a detailed implementation is introduced in our previous work. We synthesized the blink circuit's design in TSMC 28nm technology. Under 1 GHz clock frequency, it achieves 37 mega inferences per second performance and 410 picojoule per inference energy efficiency. The processing speed outperforms the Xeon E5 2860 CPU by 10.4 times and the energy efficiency outperforms the same CPU and V100 GPU by 62, 80, 93 times and 52.4 times, respectively. According to the synthesis results, the proposed bit-sparse quantization and circuit design help reduce the circuit area and power consumption by 38.7% and 38.4% respectively, compared to the conventional design in 16-bit fixed point. Finally, we show our demonstration work on the FPGA. For the image enhancement, the morphological opening we adopted consists of two consecutive steps: the morphological erosion and the dilation. These two operations are equivalent to the min and max filtering in 2D. We designed customized erosion and dilation accelerators for them. Our accelerator makes use of the two-level reduction array structure to improve the efficiency by saving the hardware cost, and the accelerator can achieve 1 pixel per cycle throughput. This figure shows the accelerator design for the calcium trace accelerator. This accelerator is made up of a chain of tracing element called TE. The input of the accelerator is the downsampled enhanced image stream, which is fed into the accelerator in fine-grained pipeline at 1 pixel per cycle throughput. Binary cell masks are stored locally in each TE, and the tracing task finishes as the image flows through the chain of TEs. Considering 300 MHz clock frequency, the processing latency for the downsampled QVGA image is about 0.3 milliseconds. This slide summarizes the FPGA hardware utilization and its breakdown for each processing stage. The whole design can run on low-power FPGA platform Ultra 96 at 300 MHz. Under this frequency, the enhancement and trace extraction accelerators achieve 18.1 times and 2.4 times speedup over the evaluation on the 12-thread CPU. The runtime for processing one frame of calcium image is 2 milliseconds, whereas sub-millisecond processing latency can be achieved as part of the image processing and image readout can be overlapped. We built a user interface for the proposed prototype on FPGA, and this slide shows a quick demo of the real-time trace extraction from calcium images recorded from the user interface. The user interface can send commands to and receive images and traces from the FPGA through the Ethernet connection. The proposed prototype can extract calcium traces from up to 1024 cells with sub-millisecond processing latency. This concludes my presentation. In this presentation, we present an algorithm hardware co-design for real-time and embedded calcium image processing based on the LSTM inference. We propose the bit-sparse representation approach to save the circuit's area and increase energy efficiency for the LSTM inference, which we believe has a wider impact on other applications as well. Finally, we demonstrated the first real-time calcium image processing system with 1024 cell tracing capacity and sub-millisecond processing latency on FPGA platform. Thanks for the funding support, our project leader and collaborators, And thank you very much for your attention.